So in the last class, we were discussing the model concept. So, and from the propositional logic point of view, we have already seen what is a model, what is an interpretation. These things we have already seen from the propositional logic point of view. Now today we will see all these concepts from first order logic point of view. So let's let's see. So what is a first order logic that you already know? In first order logic, basically, okay, in this first order logic, FOL, this first order logic, this is also called predicate logic. In this, we have all the concepts of propositional logic, all the operators, all the connectives, propositions, everything. And together, we have some additional concepts. For example, predicates, quantifiers. Okay, we have quantifiers, we have predicates. Okay, and we have functions, relations, many things we have in first order logic. So now let's talk about the validity. Let's talk about the truth of a first order logic sentence. Okay, so let's see. Now, as I told you, if you have a first order logic statement, consider this statement. Let me give you. So g1, this g1 is a first order logic formula, and this is for all x, for all y, pxy. Let's assume this is your g1. Now what we can say about g1? So this formula, what we can say about it? Can we say that this is true? Can we say this is false? So you can see that if I ask you what is the truth value of g1, then you need to know what is the domain of each of these variables. We have two variables x comma y. So you need to know what is the domain of these variables. Also, you need to know what is this predicate pxy. Okay, so basically this information you need to know before you can answer the truth value of g1. For example, consider now I am giving you the domain of x comma y, and let's assume the domain of x comma y is set of natural number. So this natural number means basically this 1 2 3 and so on. This is your domain of x comma y. Okay, and let's assume that the pxy is given to you, and this pxy is x greater than y. Okay, so now you have the complete information. You have the domain of x comma y, you have the predicate pxy. Now if I ask you what is the truth value of g1, you can very easily answer it. So what will be the answer for the what will be the answer? What is the truth value of g1? So you can see truth value of g1 is false. So it will be false. Now, because why it is false? Because you can see this is your pxy predicate, and this is your set of natural number. So in this g1, he is saying for all x, for all y, means basically for all pairs, this pxy must be true. This is what g1 is saying. But you can see that for this pair, consider this pair 3 comma 4. For this pair, if you see p3 comma 4 is false, because 3 is not greater than 4. So you can say that this g1 is false. The truth value of g1 is false. But remember, the truth value of g1 is false only in this environment. So this is the environment I have given to you. We will call it environment. Okay. So we will call it environment. In this environment, this g1 is becoming false. I can give you a different environment in which this g1 can become true. Consider this another. So let's call this environment e1. So this is environment e1, and let's take environment e2. And in this environment, what we have, the the domain of x comma y, let's take that set of natural number, the same 1 2 3 and so on. This is set of natural number. This is the domain of x comma y. Now let's take px comma y, and this px comma y is basically, you can say that what is this px comma y? You can say this is x plus y greater than 0. This is our px comma y. Now you can see that in this environment, if you consider this environment e2, in this environment this g1 will become false. Sorry, this g1 will become true in this environment, because in this g1 what he is saying that for all pair, for all x, for all y, means all pair x comma y, this pxy must be true. Yes, in this environment e2, you can see the domain of x comma y is set of natural number, and the predicate pxy is this. So in this environment, this pxy is true for all x comma y, whatever you take. If you take 1 comma 1, then you can see 1 plus 1 is greater than 0. If you take 3 comma 4, 3 plus 4 is greater than 0. So hence we can say that in this environment E2, this G1, the truth value of G1 is true. Now, what can you say from this observation? So, like we have a first order logic formula. So this G1 is a first order logic formula. Now, for this first order logic formula, we have two environment E1, environment E2. In this environment E1, this formula is becoming false. So in this environment, you can say this G1 is becoming false. And in this environment E2, this formula is becoming true. So, and one more thing, in the propositional logic, when we were discussing this model concept from the propositional logic point of view, at that time we have seen what is the interpretation. So the definition of interpretation, we have seen that interpretation is nothing but basically the information that we need to find out the truth value of a formula. So in the propositional logic, in the last lecture, we have already seen that every row in the truth table, okay, that was a interpretation. But coming to first order logic, the interpretation, what are the things that you need to answer the truth value of any first order logic formula? So these are the things you need. One is, what is the domain of each variable? You have two variable x comma y. So we need to know the domain of each variable. So this is the first thing. Okay. Now I can say that basically you need domain. After knowing this domain, you also need to know what what is the meaning of each predicate. Like here we have pxy. This is the only predicate we have. So we need to know what is this predicate. So basically we need to know what is domain, and also we need to know what are all the predicates. And if there is anything else in this formula, we should know about it. So basically, if you have these two things, then what you can say? You can say that after having this complete information about this formula G1, this is called environment of G1, or you can say this is basically your interpretation of G1. So either you can call it environment, or you can call it interpretation of G1. So in this interpretation, like in this interpretation, this G1 is false. In this interpretation, this G1 is true. Okay. So now we have the definition of model. What is the definition of model? Model is an environment in which our formula is true. So for example, in this environment E1, our formula G1 is false. So this E1 is co-model. So this E1 is basically this E1 is co-model for G1. For this formula, this environment E1 is co-model. What is the definition of co-model? Co-model is an environment in which our formula is false. And what is model? Model is an environment in which our formula is true. So for example, for this formula G1, this E2, this environment E2, this is a model. So this E2 is a model. Okay. So now we have the definition of model, and what is the definition of interpretation. So remember this, either we can call it environment, or if we can call it interpretation. Like most of the books actually they call it interpretation. So like this is an interpretation, you can see. So but anyway, just to give you some intuitive idea, I am using these words like environment. But anyway, this is one possible interpretation. This is another possible interpretation. In this interpretation E1, our formula is false. In this interpretation E2, our formula is true. So that is the complete point. Now we will solve many questions, so it will be clear. You don't have to worry about these concepts. If anyone has any doubt after half an hour, then you can ask. Let me just cover all the concepts first. So in first order logic, what is a first of all we will see what is a model. But anyway, before we look at model, you can see that if you have any first order logic formula, let's call the formula G1, then what are the information that you need? You need what is domain. Also you need what is the interpretation of each each symbol that we use here. For example, if we use a predicate here, then we need the information about that. If we use any other relation, function, anything we use in this first order logic formula, then we need information about that. So basically, this domain we need and interpretation we need. Okay. And one more thing, in complete mathematical logic, by default, domain is always non-empty. So in the question, if they do not give you any information about the domain, then what you need to consider, the domain by default is always non-empty. Explicitly, if they mention, let's assume they explicitly mention that domain is empty, D is empty, then you need to consider empty domain. Otherwise, domain will always contain at least one object. Domain will always be non-empty by default. Okay. And you can see, so once you have a domain, for example, this domain is set of natural number, then what you need interpretation. And what is interpretation? In this interpretation, you need information about each symbol. For example, if you have a predicate symbol, then you must know what is that predicate symbol. If you have a constant symbol, then you must know what is that constant symbol. If you have a function symbol, you must know what is that function symbol. So these information you need, then only you can answer, you can find the truth value of a first order logic formula. Okay. And you can see here, M is a model of sentence alpha if alpha is true in M. So this is important. This is the definition of model. In this, basically he's saying that if you have an environment, then that environment will be called model of our formula. Our formula is alpha. Let's assume this is our formula. So this is first order logic formula. For this first order logic formula, we will say that M is a model. For this formula, M is a model. If this formula is true in this M, in this environment M, this alpha must be true. Then this M will be called model. And what is co-model? For this alpha, we will say that M dash is co-model. This M dash is co-model if this alpha is false in M dash. So that is the definition of model, and that is the definition of co-model. Let's take many questions we will take and we will try to see. So let's first see what is this universal quantification. This you already know. Universal quantification means for all x px. Okay, basically for this x you have a domain. Every variable in our you can say every quantified variable, for example this for all x px, so this x is a quantified variable because this x we are applying this quantifier over this variable x. Okay, so that's why this x is called quantified variable, and every quantified variable has a domain. So let's assume this is the domain. Then what is the meaning of this for all x px? The meaning is simple. For every element in the domain, this px must be true. So that is the meaning of universal quantification. Okay, here you can see for all, and then you have some variables, and then you have some sentence. Basically, we want to say that for all elements in the domain, this sentence must be true. That is the meaning of universal quantification. Okay, and for example, let's assume that this is your English statement, and we want to convert this English statement into first order logic formula. So this is the statement: everyone at the University of Maryland is smart. So basically he want to say that for all, basically this statement we can rewrite like this: for all x where x is basically in the University of Maryland. You can say x is in University of Maryland, you can say. Okay, then x is smart. So this is what it wants to say. Okay, you can say for all x, if x is in University of Maryland, then x is smart. This is that statement. Now you can very easily convert it. For all x means for all x. Now inside what he's saying if x is in University of Maryland, means basically at x comma University of Maryland. It means this is a predicate, remember. And what is the meaning of this predicate? It will be given to you in GATE exam. In any exam they will give you what is the meaning of this predicate. So let me tell you the meaning is this: X is at the University of Maryland. This is the meaning of this predicate. So I can say that if X is in University of Maryland, then X is smart. Means if this, then it implies X is smart. Smart X. This is how you can convert any English statement into any you can say this for all statement. Okay, universal quantified statement. If you have, then you can convert it into first order logic formula. This is how you can convert. Okay, so this you already know. These are the basic concepts that I think you already know. In the last class also we have seen some of these concepts. So for example, what is this existential quantifier? You know, in this existential quantifier, basically we say that for at least one value in the domain, our this sentence must be true for at least one value. Now if you have an English statement, then how can you convert it into, like here you can see this is the English statement and this is a existential statement. He's saying someone at UMD is smart. Someone means basically at least one student, at least one person in at UMD is smart. So I can say that there exists this same statement. I can rewrite like this: there exists X at UMD who is smart. So this is how I can rewrite. Or I can again I can rewrite like this: there there exists X such that X is at UMD and X is smart. This is how I can rewrite it. And now I can convert it into our formula very easily. For all X, X is at UMD and X is smart. Means basically you can say that at X comma UMD means X is at UMD and X is smart. So this is how you can convert this statement into formula, into first order logic formula. One thing you can notice that when we were dealing with universal statement, when we were dealing with for all statement, at that time we were writing like this: for all X, then something Px implies Qx. So you can see that when we were dealing with for all statement, at that time we were using this implication. And when we are dealing with their exist statement, at that time we are using conjunction like this: Px and Qx. Because this statement says that for all X, if X satisfies property Px, then X satisfies the property Qx. Okay, like in the previous statement, in this statement you can see here we are using it. Because in this statement, if you read, this is saying everyone at UMD is smart. What it means? That if you are at UMD, then you are smart. So that's why we are using implication. And in this statement, you can notice that in this statement, he's saying someone at UMD is smart, means at least one person at UMD is smart. There is at least one person X who is at UMD and who is smart. So that is the point, and that is why with there exist, generally we use conjunction, and with for all, generally we use implication. Okay, these are the very basic things that you already know, but our main chapter for today's class is model. Now, what is a model? Let's come back to it. So, in the first order logic language, in the first order logic, basically, first you need domain for each variable. In this domain, what you do? In this domain, you will have elements, and for these elements, you will interpret all the formulas for these variables. Okay. So now, now in this domain, you have interpretation. What is the interpretation? Interpretation is basically all the information that you need to answer, to find out the truth value of a first order logic formula. So you can see now, if we have domain and we have interpretation, these two things we have domain and we have interpretation. then this we will call, either we will call it environment or we will call it structure. So let's assume we are calling this M. So this domain plus interpretation, let's call it M, and this M is environment. Now this environment will be called model if our formula is true in this environment. If for this domain and this interpretation, if our formula is true, then we will say that our this environment M is a model. Okay. Now, so basically you can see that it provides all information we need to determine the truth value of each sentence in our language. So that is the complete point. What is the environment? Environment has all the information that we need to determine the truth value of each sentence in our first order logic formula, in our first order logic language. So that is the theory. So far we have seen theory. Now let's take many examples I am going to take, and we will see how these things work practically. So let's take example. Let me take question 1. Consider this formula G1, and this formula is basically there exists x for all y pxy. This is the formula. Now for this formula G1, you need to find out model and you need to find out co-model. So basically you need to find out for model for G1. Also you need to find out co-model for G1. You know what is a model? Model is an environment in which G1 is true. Co-model is environment in which G1 is false. Can you find out? Try this. Try to think about it. In the previous lecture, in the last lecture, we have already seen this example. This is a nested quantifier. This is saying that for every x, there exists x such that for every y, pxy must be true. It's like this. Let's assume this is the domain of x. So let's call it D1. And let's assume this is the domain of y. Let's call it D2. Then this is basically saying that there exists x and for all y. So like this pxy must be true. So this is the meaning of this nested quantifier. We have already seen this in the last lecture. So let me give you model for G1. The model I can very easily find out. You can take domain. What are the information that we need? We need a domain for each variable. So let's take domain to be set of natural number. For x and y both. For this x also this is the domain, and for y also this is the domain. So this is the first thing we need. We need a domain. We have a domain. Now I also need to define what is this pxy. Basically I need interpretation of pxy. What is the interpretation of pxy? So I can take pxy like this. Remember, I want to find out model, and model means I want to find out environment in which this formula G1 must be true. So let me find out. So you can say that this x is less than or equal to y, and this domain is set of natural number 1 2 3 and so on. This is the domain, and this is our pxy. Now tell me, can we say that this environment is a model? Tell me yes or no. Can we say this domain and this interpretation, can we say that this complete environment is a model? Yes or no? So you can answer it very easily. Let me answer. So the answer will be yes. This is a model, because in this environment our formula G1 will be true. You can see, because this is the domain for each variable, and this is pxy. X is less than equal to y. So you can see that our G1 will be true. Why? Because this x you can take to be 1, This you can take. Now you can take everything, because 1 is less than equal to 1, 1 is less than equal to 2, 1 is less than equal to 3, and so on. So that's why you can see that this formula G1 is true. So I can say that this environment, this is model for G1, because G1 is true in this environment. Now let's find out co-model for G1. Can anyone suggest any co-model for G1? Remember the definition of co-model. Co-model is an environment in which this formula G1 will become false. Can you provide any such environment? Anyone want to try? You can write in the chat box. I can see this. Okay, let me give it to you. Again, the first thing you need is domain. So let's take the domain to be set of natural number. The same thing. Okay, this is our domain for both variables, for x, for y. For both variables, let's assume that this is the domain, set of natural number. Now, I also need interpretation of pxy. So let me give you interpretation of pxy, which will make this G1 false. So let me take this. X is less than y. Let's take this. Now, you can just check it out. In this environment, our G1 will become false. Because you can see this is the domain 1, 2, 3, and so on. This is set of natural number. This is the domain, and pxy is x less than y. So this G1 will become false, because G1 says that there should be at least one element. There should be at least one element which is less than every element. Which is less than every element. So we don't have any such element. For example, if you take 1, then remember this 1 is not less than 1, even though 1 is less than 2, 1 is less than 3, 1 is less than 4, but 1 is not less than 1. Similarly, if you take 2, now you can see that 2 is not less than 1. So that's why you can say that no such x we have. There is no such x. Hence we can say that for this formula G1, the co-model is this. This environment is the co-model. So we have model for G1, we have co-model for G1. In this scenario, this G1 will be called satisfiable. This G1 is called satisfiable because actually, like you can see from the definition of propositional logic. In propositional logic, what we were doing in this propositional logic, if you have a formula of propositional logic, let's assume that you have a formula G1, this is the formula. Then what is the definition of satisfiability? Satisfiable means at least one row which will make it true. We want to satisfy this G1. So at least one row, at least one truth assignment which will make G1 true. Similarly, in first order logic, what is the definition of satisfiable? The definition of satisfiable is very, so basically the definition of satisfiable in propositional logic we have already seen in the last class. And the definition of satisfiable in first order logic, what is that? That is basically if there exists a model for our formula, for this formula G1, if there exists a model, then this formula G1 will be called satisfiable, because we can satisfy it. Satisfy means we can make it true. If you can find at least one model, if you can say that, if you can prove that there exists at least one model, then you can say that this G1 will be satisfiable. And what is the definition of unsatisfiable? Unsatisfiable means we cannot satisfy it. So in propositional logic, what is the definition? For every row, this G1 must be false. Or you can say that whatever truth assignment you give, whatever truth assignment you do then this G1 should evaluate to false. Then we will say that this G1 is unsatisfiable. Now in our first order logic, what is the definition of unsatisfiable? The definition is basically if there does not exist any model. I can say there does not exist a model. Or you can say basically all model are all environment are co-model. Either you can say there does not exist a model, or you can say all environment are co-model. All environment are co-model. So this is the definition of unsatisfiable. Now you can see that this formula G1, this is satisfiable because there exists a model. Like this environment, if you consider this first environment, if you consider, then this environment is model for G1. So this G1 is satisfiable. Okay, so very easily you can see. Now the second thing, now next concept. The next concept is, after satisfiability concept, we have the concept of validity. In the last class, we have seen the concept of validity from propositional logic point of view. In propositional logic, if you have a formula G1, then we will call it valid. Remember, in propositional logic, valid means always true. Valid means always true. And always true means tautology. This always true. In propositional logic, this is the definition of valid. If your formula is always true for all rows, what in your truth table, for every row, your formula G1 is true, then we will say that this G1 is valid. Similarly, in first order logic, what is the definition of validity? Very simple. All environment are model. If all environment are model, whatever environment you give, all environment are model. Okay, then we will say that this G1 is valid. For example, you can see that this G1, if you see here, this environment is co-model. So at least one environment is co-model. Hence you can say that this formula G1 is not valid. This is satisfiable. This G1 is satisfiable because we have a model. But this is not valid. This is invalid, or you can say this is not valid because there exists a co-model. So that is the definition of validity, satisfiability, unsatisfiability. These are the concepts that we have. Okay, model, interpretation, domain, all these concepts we have seen. And now let's take examples. So first of all, you can see if you have a formula A, then that formula will be called satisfiable. When do we call it satisfiable? Satisfiable means for some structure, as I told you, we are calling it environment, but we can also call it structure. And we are calling it environment. We can also call it structure. Okay, so you can see that what is the definition of satisfiability? If you have a formula A, that will be satisfiable if for some structure, at least one structure, in this structure, this formula A must be true. Means you can say there exists at least one environment which will make our formula true. So there exists at least one environment, there exists at least one structure which is model, So that is the definition of satisfiability. And what is the definition of validity? Validity means all structure must be model. Every structure must be model. And what is the definition of falsible? Like basically, uh, falsible means there exists a co-model. This means basically we can make it false. We can make our formula false. So you can say there exists a co-model. Co-model is also called counter model. So in short, we call it co-model, but this is also called counter model. So if there exists a co-model, then we can say that our formula is falsible, falsifiable, whatever you can read this, whatever is the pronunciation. Okay, we can make it false. That is the point. So we have seen all these concepts. Now let's take many examples. Consider this formula. So question 2. We have already seen one question. Now let's second question. there exists xpx, very simple, there exists xpx, let's call it g2. So this is our formula g2. Can anyone tell me, is it satisfiable? Is this formula satisfiable? Yes or no? Is this formula satisfiable? So let me tell you, yes, this is satisfiable. So this formula G1, this is satisfiable. But remember, if I say that this is satisfiable, then I need to give you model for this formula G1. So let me give you environment in which this formula G2 will become true. So let consider this environment. So consider this environment E1. This is an structure or environment E1 I am giving you. So what I need domain for x. So let's assume the domain for x is set of natural numbers. Actually, you don't have to take always set of natural number. You can take something else you can take. For example, consider this domain A, B, C. This is the domain you have. And I am giving you, after this domain, what we need? We need interpretation of Px. So let me give you interpretation of Px. So let me give you that PA is true, PB is false, and PC is true. Consider this interpretation. So this is the interpretation of Px I am giving you. So this is the domain. Domain has three elements A, B, C, and this is the interpretation of Px. Basically, I'm giving you that PA is true, PB is false, PC is true. Now this environment E1 is a model, you can see, because in this environment this G2 will become true. You can see very easily, because there exists element in the domain, for example this A, for which this PA is true. So there exists element in the domain for which this predicate P is becoming true. So yes, you can say this G2 will become true. In this environment E1, this G2 will become true. So this environment E1 is a model. This is a model for G1, G2. This is a model for G2. Now let me give you another environment in which this formula G2 will become false. Can anyone tell me? Can anyone give me one suggestion? Can you give me environment in which this formula G2 will become false? So let me give you. So very easily you can consider. For example, you can consider this domain ABC, the same domain you can consider. And let me give you interpretation. Because what is the meaning of environment? Meaning of environment is basically domain you need, and you need interpretation of each symbol. Like here we have this P, this is the predicate we have. So we need interpretation of this P. So let me give you interpretation of P. Like PA is false, PB is false, and PC is false. Consider this environment. In this environment, in this structure E2, you can see that G2 will become false. In this, because this G2 will become false, because in this domain, for every element P is false. So we do not have any element, at least we do not have at least one element for which P will become true. Hence, you can say this G2 will become false. So in this environment E2, this G2 will become false. So what you can say? You can say that this G2 is satisfiable because we have at least one model. Also, this G2 is not valid. Not valid. Why this is not valid? Because validity says that every environment must be model. But you can see this environment E2, this is not a model. So this is not valid. Also, we can say that there exists a co-model. This E2 is a co-model. Remember, this E2 is a co-model. So we can say that there exists a co-model. Hence, you can say that this formula G2, this is, we can make it false. So we can call it falsifiable. Whatever. Falsifiable means we can make it false. Somehow you can make it false. So because there exists a co-model, hence this is falsifiable. This is not valid, and this is satisfiable. So this is how you can check. So this was the next example. Now let's take question number 3. As I told you, we are going to take many questions and you will get all the concepts. So you don't have to worry about it. So consider this formula for all x, px or not px. For all x, px or not px. Can anyone tell me, is it valid? Is it valid? This is my question. Is it valid? This is the formula you have. Let's call it G3. Let's call it G3. So this G3 you have. Can you tell me yes or no? This is valid or not? Yes or no? So you can think about it. This is actually valid. What is the reason? Because he's saying basically this formula G3, what it is saying? It is saying that for all x, either px or not px. For everyone, either px or not px. So you can see that this is always true. Whatever domain you take, consider any domain, whatever domain you want to take. Consider this domain A, B, C, D. Now, in this domain, you can see that whatever domain you take, that is your wish. You can take any non-empty domain you can take. You will see that this px or negation px, this will always be true. Okay, for example, maybe you make this PA. What you will make this PA? If you make this PA true, then this will become true for A. For A, this PA will become true. For B, let's assume you make it false. You make this PB false. Then what will happen? Then this will become true. Negation of PB will become true. So that is the point, that whatever environment you take, whatever domain and whatever interpretation. So domain plus interpretation, whatever environment you will take, you will see that this formula G3 is always true, because this internal thing, if you see, this internal thing is like this, P or negation P. And you know this P or negation P, this is always true. Either this will happen or this will happen. Okay, either this will be true or this will be true. So that's why this internal thing is always true. So you can say that for every x, this will always be true. So this G3 is always true. This G3 is valid. Valid means this G3 is always true. In every environment, this G3 will be true. Whatever domain you take, whatever interpretation you take, you will see that this G3 will be valid. So you can say that every environment is model. Whatever environment you will take, every environment is model. So because this is valid, so this is satisfiable also. Because if every environment is model, then definitely you have at least one model. Satisfiable says at least one model. Valid says all environment must be model. So this is satisfiable and this is valid. And you can see we cannot have any counter model. For this G3, we don't have any counter model because every environment is a model. So you can say that this is not falsifiable. Falsifiable. We cannot make it false basically. This G3 we cannot make it false. So this is the properties of G3. Let's take the next question, question number 4. And this question number 4 is, yes, for all x px or for all x negation px. This is the next formula that we have. Can you tell me, is this valid? Yes or no? Is this valid? Try to think about it. Is this formula valid? So this is not valid. This formula Q4, this is actually invalid, because let me give you co-model for this. So let me give you co-model for this. See, this is saying that for every x, either px should be true, or for every x, px should be false. So the co-model will look like this. Let me give you environment which will work as a co-model. Consider this situation. Let's assume you have A, B, C. These three things you have in your domain, A, B, C. Now consider that PA is true, PB is false, and PC is true. Consider this scenario. So this is the domain you have, domain for X. This is the domain for X. And this is the interpretation of PX. PA is true, PB is false, PC is true. Now, in this environment E2, you can see this Q4 will become false. Why? Because in this environment, in this interpretation, you can see that this for all x px, this will become false. So this first part, for all x px, this will become false because PB is false. So that's why you can say that for all x px, this will become false. Also, you can see that this for all x negation px, for all x negation px, this will also become false. Why this will become false? Because this is saying that for every x, px must be false. But you can see PA is true, PC is true. So you can say that this second part is also false. This first part is also false. And you know, false or false, that is also false. So completely this Q4 is false. In this environment E2, this Q4 is false. So this environment E2 is basically co-model for Q4. So this is the co-model we have. Now you can see that because we have at least one co-model, so this is not valid. Now, is it satisfiable? Next question. This is not valid, but is it satisfiable? Tell me yes or no. Is it satisfiable? So let me give you environment in which this Q4 will become true. So let me give you model for Q4. So very easily you can see, consider this domain. Let's assume the domain is A, B, C. Okay. And now we need interpretation for PX. So let's assume PA is true, PB is true, and PC is true. So this is the domain, and this is the interpretation of P. PA is true, PB is true, PC is true. Now this is the environment you have. You can see that in this environment, Q4 will become true. Why? Because for all x px, this will become true. Because for every element in the domain, Px is true, Pa is true, Pb is true, Pc is true. So this for all x Px, this will become true. And this for all x negation Px, this will become false. This will become false. But this is or, true or false. This is or. True or false is true. So what you can say? You can say that this environment E1, this is model for Q4. This is model for Q4. So for this Q4, we have at least one model. We have at least one co-model. So you can say this is not valid. This is satisfiable because we have at least one model. Okay. And yes, of course, this is falsifiable because we can make it false. Like this in this environment E2, this is false. So we can say that this is falsifiable. This is falsifiable. So this is how you can check it out. Let me take another next question, that is question number 5. And this is for all x Px and for all x negation Px. Remember, in the previous question, we have disjunction here. In this question, we have conjunction. So this is your formula. Is it satisfiable? This is the first question. Is it satisfiable? Yes or no? So you can see this is not satisfiable. Let me tell you why. Because if you take any environment, then both these can never be true. Like, see, how to make it true? We have to make this true and we have to make this true. But we can never make both of them true. Whatever domain you take. But remember, by default, remember, domain always is non-empty. So whatever non-empty domain you take, for example, consider this domain A comma B. Now let's try our best. Let's try to make this true and this true. Let's try to make this and this both true. So if I want to make this true, then what I will have to do? I will have to make P true and I have to make PA true and PB true. So I need to, I have to make PA true, PB true. But if I do this, then this will become true, but this will become false. Because if for every variable, if P is true, then what you can say, this for all x negation Px, this will become false. So if I try to make this true, then this will become false. And if I want to try, if I want to make this true, then this will become false. So that is the point. If you have single element, let's assume you have single element. Now, if you make PA true, then you can see that this first part will become true, but the second part will become false. If you take PA equal to false, then this second part will become true, the first part will become false. So ultimately, the point is that either you can make this true. If you make this true, then automatically this will become false. If you make this second part true, then automatically this first part will become false. So you can say that this conjunction will always be false. So this is not satisfiable. Now the next question, is it valid? See, this is not valid because this is not even satisfiable. So this is not valid. Valid says that all environment must be model. And satisfiable says that at least one environment must be model. This formula Q5 is not satisfiable. What it means? It means that we do not have any model. If we do not have any model, then this is not valid also. So this is not valid. Okay, so that is the complete discussion. So this was the Q5. Now you can try to solve many questions on your own. Okay, so these slides, these questions I have done, and you can try to solve the remaining questions. These questions you can take as homework. And now let's move on to the next type of question. Okay, so these you can take as homework. So if you have any doubt in these questions, these homework questions, then you can ask in the next lecture. You can ask. Okay, the answer is also there, like this formula, this is not satisfiable, this formula is valid, and this formula is not valid. So all these answers are there. You just need to convince yourself, like this is not satisfiable, so you need to find co-model. This is valid, so you need to prove that every environment is a model. This is not valid. Not valid means you need to find counter model. So this thing you can take as homework. Let's take this is the 2018 question. This is GATE 2018 question. This is a famous question because in the GATE exam only two times they have asked a question from model. Only two times, in GATE 2018 and in GATE 1991. So there are only two questions. But because this is a very recent question, so that's why students, like we have this probability, we have this huge probability that they can ask again, because this is a recent question. But anyway, let's try to solve it. Now before I solve this question, let me solve some other question, because automatically you will be able to solve this GATE 2018 question. Consider this. Now this is my question. So you have a formula G1. So this is a formula G1, and this is basically there exists X, there exists Y for all Z, P, X, Y, Z. So this is your formula G1. So you can see there exists X, there exists Y for all Z, P, X, Y, Z. Now for this formula, let's assume I give you, this is the given information. The given information is that there exists a model of size 3. So this is the information that is given to you. There exists a model of size 3. Let's assume that each variable has same domain. Okay, so each variable has same domain. Let's assume that. So this is the, so let me, basically this is given that there exists a model of size 3. Size means universe. And let me also give you that every variable has same domain. So this is the information that is given to you. Now, the question that we are asking, can you guarantee, this is the question, that can you guarantee that there exists a model of size 3? This is the question. There exists a model of size 2. Can you guarantee that? So this is the question. So let me explain this question. So this is the formula that is given to you, G1. There exists X, there exists Y for all Z, Px, Yz. And this is the information that is given to you. Information is that there exists a model. There exists a model of size 3. Size 3 means basically domain has 3 elements. Basically, you can say that the domain has 3 elements. So you can say the domain has 3 elements. And every variable has same domain. So this is the information that is given to you. Now we are asking, can you guarantee that there will definitely exist a model of size 2. Size 2 means domain of 2 elements. So let's try to solve it. So see, this is the formula G1, and in this formula G1, this is there exist. So we have already seen in the last class. So the domain of X is, this size is given to you. So there exists a model. So let's assume that model is, this is the domain. Let's assume A, B, C. This is the domain. So A, B, C, this is the domain. For Y also, this is the domain. and for Z also this is the domain. So this is the, now he's saying there exists X, means there exists at least one element. Let's assume that element is B. Now he's saying there exists Y. There exists Y means you can, here also there exists Y means at least one element. Let's assume that element is this. Now he's saying that this B, A, now he's saying for all Z, for all Z means now this, for these things, for these triples, this PXYZ must be true. This is given to you because in the question he's saying there exists a model of size 3. Now we are assuming that this is that model, means this is the domain A comma B comma C, and now he has given that in this domain we have at least one interpretation such that this G1 will become true. So basically let's assume this B, from here we are taking this B because he's saying there exist. From here we are taking A because he's saying there exist, and from here we are taking everyone because he's saying for all Z. So for these things, for this BAA, for this BAB, for this BAC, for these three triples, PXYZ is true. This is true. This is the information given to you. So far we have only taken the given information and we have understood what is the meaning of this given information. Now we want to find out, can you guarantee that there exists a model of size 2? Yes, you can guarantee. Because what you can do, you can consider this B comma A. Consider this B comma A. So let me take next slide. So consider this B comma A. Consider this domain B comma A. In this domain, can we guarantee that our formula G1 will become true? Yes. Why? Because, so what we are taking B comma A. So in this B comma A, already these three things you already have. Okay, like BAA, BAB, BAC. For all these three triples, our formula is already true. So now take B comma A. You can see that this is your A comma B, this is your A comma B, and this is your A comma B. Okay. Now, from we want to show that in this domain we have at least one interpretation which will make our formula true. This we want to say. This is our formula. So very easily you can see from here you can take B, from here you can take A. Now you can see that for this BAA, for this BAB, for these two things already we have seen, already it is given to us that for this BAA and for this BAB, for these two things already our formula is true, already our P is true. So for these things P is already true, that is given to us. So what you can say? You can say that in this domain we have made this G1 true. You can see definitely we can make this G1 true. So we can guarantee that there will exist a model. So is this question clear? Like some maybe, okay, this is the first example. So maybe some of you did not get it. We will take more examples and it will be clear. Don't worry. So my point is that we can guarantee that there will exist a model of size 2. Okay. All you have to do is just take this A comma B. Why I am taking this A comma B? Because you can see this A was corresponding, this B was corresponding to X, this A was corresponding to Y. Because here you can see this B, we were taking this B for this X, for this existence of X. We cannot guarantee a model of size 4. That we cannot guarantee. Let me prove it to you that we cannot guarantee a model of size 4. So anyway, right now you can see for this there exists X, I am taking this B, and for this there exists Y, I am taking this A. So that's why I am taking this A comma B, because I know that for this A comma B, definitely this will become true. This G1 will become true. So that's why I am taking A comma B, and in this in this domain a comma b, my formula g1 is true, so I can say that we can guarantee that there is a model of size 2. Now next question, let's take the next question, that is, can we guarantee that there is a size model of size 1 for this formula g1? Can we guarantee that there is a model of size 1? Let's see. So this is the g1, that is, you have, there exists x, there exists y, for all z p x y z. So this is the formula that you have. This is the formula g1 you have, and for this formula it is already given to you that there is a model of size 3. Now my question is, what is my question, that can we guarantee that there is a model of size 1? So let's see. What I will try to do, I will try to make it false. I will try my best to not have any model of size 1. So what I will do, see, this is already given to you that we have a model of size 3. So again, let's consider a comma b comma c. Again a comma b comma c. Again a comma b comma c. He's saying there exists x. So take this a. Now he's saying there exists y. Now take this b. Now he's saying for all z. For all z means this. He's saying that for this a, b, for all these things, this pxy is true. What he's saying, basically he's saying that for this a b a b b, a b c, for these three things, for these three triples, he's saying it is given to you that pxy is true. So this is true. Now can you say that can you guarantee that there is a model of size 1? So let's consider model of size 1. So consider this model. Size 1 means only one element. So consider this. Now for this domain, can you say that this will be true? Let's see this. So for this domain, for this domain, let's see. So because we have only single element, Now can you guarantee that there exists x, there exists y, for all z, pxyz, this will become true? So because there is only one element here, we have to take it. There is only one element here, we have to take it. So basically finally we have PAAA. Now can we guarantee that this is true? No, because you can see this is the given information, and in this given information ABA is true, ABB is true, ABC is true, but AAA is not true. So let's make it false. PAA, let's make it false. So that's how you can see that if we have this scenario, then we cannot guarantee that there will exist a model of size 1. You can either take this, or you can check out for this also, Whatever single element model you take, whatever single element domain you take, you can see that we cannot guarantee that we have a model of size 1. Okay, so that is the point. Hence we can say for this G1, if there exists a model of size 3, then we can guarantee that there will exist a model of size 2, but we cannot guarantee that there will exist a model of size 1. Now let's check out whether there exists a model of size 4 or not. So again, this G1, there exists x, there exists y, for all z, p, x, y, z. Already the given information is that there exists a model of size 3. Let's assume that this is a comma b comma c. This is our assumption. Now the question, what is the question? Can we say that there exists a model of size 4? Can we guarantee? So again, I will try to make it false. I will try to make a domain of 4 elements, and for that domain of 4 elements, I will try to prove that there is no model. So from the given information, we have this situation. Okay, AB, ABC, ABC, the same thing we have repeated many times, but anyway. So there exists x, let's assume you are taking b from here. There exists y, let's assume you are taking a from here. they for all Z. So for basically this is the situation. Means it is the given information that for this BAA, for this triple, for this BAB, for this triple, and for this BAC. So for these three things, it is already given to us that we have a model. So this P is true. So this is the given information. Now let me take A, B, C, D. I want to prove that there is no model of size 4. I want to prove that. Okay. Sorry, I want to show you that we cannot guarantee that there will be a model of size 4. This is what I want to prove, that we cannot guarantee. Of course, there may or may not exist, but we cannot guarantee. Okay, so that is the point. So for example, let's assume A, B, C, D, these four elements you have. Now A, B, C, D, A, B, C, D, A, B, C, D. Now let's see whether we can guarantee that there will exist a model or not. So again, you like it is already given to you. Like for example, this B is here, this A is here, and this ABC is here. So all these things are here. But to make a model, means to make this given true, what we need? We need this D also, because here we have for all Z. Here we have there exist X, so we can take this B. Here we have there exist Y, so we can take this A. But here we have for all Z, so we already have A, we have already have B, this C, but we also need to take D. But can we guarantee that this B, A, D, this will make P true? Can we guarantee that? No, we cannot guarantee, because from the given information, we only have this information that BA is true, BAB is true, and BAC is true. This is the only information that we have. We cannot guarantee. The point is that we cannot guarantee that BAD, for this BAD, this P will be true. This we cannot guarantee. Like you can think like this. Think of this A, B, C as an introvert family. Assume that this A, B, C is an introvert family. So this A, these are three people, okay, and this is an introvert family. Like and for this family, for this A, B, C, this G1 is true. Let's assume like there exists a father, there exists a mother. For all people, they are basically this PXYZ is basically means they are arranging food. Let's assume this PXYZ means arranging food. So basically this statement G1, what it is saying? It is saying that there in this family, in this A, B, C, in this family, there exists element A, which is father. There exists element B, which is mother, such that they are arranging food for everyone. This is the situation you can consider. Like if you have seen the movie, there is a movie called Wrong Turn. Okay, in this movie you can see that this is a family of you can say cannibals. So these are the cannibals, and they live in the jungle. So they are isolated from the real world, from the humans. They are isolated. These are cannibals, and what they do, they go out and they search for food. Okay, anyway, so this is an isolated family. Now for this family, this G1 is true. This is given to you because this A, B, they are arranging food for A, B, C. These two people, they are arranging food for all these three people in the family. But now can we guarantee that this A, B, they will also arrange food for four people? Now if you include, let's assume you include this is the family, but if you include a fourth people, let's assume some random fourth people you are including. Now can we guarantee that this A, B, they will arrange food for D also? It is already given that this A, B will arrange food for A, they will arrange food for B, they will arrange food for C. But we cannot guarantee that they will arrange food for D also. If this is a wrong turn movie, then actually this D will become the food. They will eat this D. So anyway, this is the like the intuition. I am just telling you that we cannot guarantee. that there exists a model of size 4. This is how you can intuitively think. If you think like this, intuitively, if you think like this, then many questions you can solve very easily. Okay. So this is the formal approach. Like this is the formula. So far we were looking at the formal approach. We were taking ABC, we were taking PA, and so on. All these things, formal things we were taking. But this is an informal approach. This is also valid approach. Like, okay, like this is how you can understand. This is how you can get the intuition of this topic. So anyway, whoever is there who has watched this wrong turn movie, he can relate to this example. Okay. So anyway, so we cannot guarantee the model of size 4. Is it clear, Sabrina? Now let's take the next question. Question number, okay, whatever. Question number 2, let's take. And in this question, let's take this for all x, for all y. Okay, before we take this question, let's take a very simple question we can take. Question 2. This is basically a formula G1 is given to you. That is, there exists x for all y, pxy. Very simple thing. Okay, this G1. There exists x for all y, pxy. Now, for this formula, let me give you the information that is given to you. So this is the given information, that there exists a model of size 2. So there exists a model of size 2. Size 2 means domain has 2 elements and we have a model. So in this domain of 2 elements, we have interpretation of P such that this G1 will become true. So this is the given information. Now the question that I'm asking is, can we guarantee that there will exist a model of size 1? Can we guarantee model of size 1? Can we guarantee that? Try this, yes or no. So let's see, can we guarantee that there will exist a model of size 1? Yes, we can guarantee. But let's see. I will try to make it false, remember. I will try to make it false. That will be my target. I will try my best to not have a model of size 1. Okay, so, but from the given information, what you have? The given information is that there is a model of size 2. Let's assume this is A comma B. So this is your A comma B. And because this is a nested quantifier, there exists x for all y. So A comma B. Sorry for the background noise. That is my niece. I can't control her. Anyway, so this is there exists x for all y. So there exists x means from here you have at least one element. Let's assume that is A. Okay. And from here, all the elements, means basically in the question it is given to you that for this AA and for this AB, for these two things, P is true. This is given to you in the question. Because in the question he is saying that there exists a model of size 2. So we have assumed that this is the domain A comma B. And for this domain, we have at least one interpretation of P such that this G1 will become true. I want to make G1 true because I want to use this given information. So to make this G1 true in this domain, what I am doing, I am taking from here, I am taking A because this is there exist. So that's why I am taking A from here. and this is for all y. So I am taking both a comma b. Now finally, I have a comma b. For these two things, this p is true. So this is the given information. Now, can we guarantee that a model of? I will try my best to not have a model of size 1. See, so what I will do, I will take this b. If I take this b, now this is b because this is the single element, so this is b. So basically, if I take this domain, then you can see that for this bb, this p need not be true. If I take this domain, remember, if I take this single element domain, then here, because there is a single element, so I have to take this b, and here is a single element, so I have to take this b. So this is there exist for all y. Okay, so this for this b comma b, this pxy, this is not guaranteed to be true, because from the given information, for a this p is true, for ab this p is true, for this bb this p may not be true. So can I say that there does not exist a model of size 1? Can I say that? No, I cannot say that. Why? Because I have to guarantee that there is no model of size 1. So far I have only proven that this may not be the model of size 1. But what about this model? What about this domain? This domain, if you take this domain, then what will happen? This is a, this is a. So for this a, already it is given that for this a, this p is true. So what it means? It means that in this domain, this g1 is true. Okay, so that's how you can say that we can guarantee that there will exist a model of size 1, and this is that model. This is that model. So we can guarantee that there will exist a model of size 1. True. This is true statement. This is true claim. So this is how you can solve it. Now, some of you might be thinking, how did I get to know that I have to take this A? See, this will come by practice. If you do a lot of practice, automatically these things will come to in your mind. Automatically these things will come. Let me give you the idea from where this A is coming, because this A is coming from here, because this A corresponds to this X. From here, this is there exist X. So for this there exist X, I was taking this A. So that's why this A will also work as model of size 1. That is the point. But anyway, this will come by the practice. Remember, this is also a domain of size 1, but this may not be a model. This is also domain of size 1, but this definitely is a model. So we can say that we can guarantee that there exists a model of size 1. If I ask you, will every model of size 1, will every domain of size 1 be a model? No, because this is a domain of size 1, but this is not a model. So this is how you can do. Now we have done, so far we have done 2 questions. In the first question, we were having like this: there exists X, there exists Y for all Z. This was our first question. And this was our second question: for there exists X for all Y, Pxy. In this question, there exists X, there exists Y for all Z. In this question, the given information was that there exists a model of size 3. This was the given information, and we proved that there exists a model of size 2. Why? Because there are 2 there exist. From here I can take, from here I can take. This there exist and this there exist. Because of these 2 there exist in the beginning, I can guarantee, we have proven it. We have done this question. So we have shown that there exists a model of size 2. In this question, he is saying there exists X for all Y. In this question, this is the given information that there is a model of size 2. And we have proven that there exists a model of size 1. Why? Because of this there exists. Okay, so that's how you can also solve this question. Like, you can take it as a homework. There exists x, there exists y, there exists z for all m, for all n, p, x comma y comma z comma m comma n. You can take it as a homework. In this question, again, this is same pattern. Remember this pattern, this pattern, this is also the same pattern, because here also we have a sequence of there exist, there exist, there exist, then a sequence of for all. This is the for all. Similarly here, a sequence of there exist and a sequence of for all. Here also a sequence of there exist followed by sequence of for all. So all these three formulas have the same pattern. In this question, if this is given to you, let's assume they give you that there is a model of size 5. This is the information that is given to you, because how many quantifier you have? 5 quantifier you have. So let's assume that this is the information that is given to you, that there is a model of size 5. Then you can guarantee that there will be a model of size 3. You can guarantee that. How can you guarantee? Because of these three, there are three there exist. Because of these three there exist, you can guarantee that there will be a model. There will be at least a model of size 3. This you can guarantee. You can take it as homework. You try to show that we can guarantee that there will exist a model of size 3. Also, we can guarantee that there will exist a model of size 4. We can also guarantee this. Wait a second. Wait a second. No, this we cannot guarantee. Sorry. Okay, we can guarantee that there will exist a model of size 3, and wait a second. Yes. We can also guarantee that there will be a model of size 4. This also we can guarantee. Size 3 model also we can guarantee, but size 2 model we cannot guarantee. So this is your homework. You can take it as homework. I am giving you the answer. So the question is this. This is the formula that is given to you. And for this formula, this is the information that is given to you. There exists a model of size 5, universe 5, domain has 5 elements. There exists a model. This is the information that is given to you. Now you need to prove, you need to show that there will definitely exist a model of size 4. There will definitely exist a model of size 3. But also you need to show that there may not exist a model of size 2. So this is how this you can take it as homework. But anyway, from this, if you understood these three examples, then you can solve this question. This GATE 2019 question you can solve. Sorry, GATE 2018 question you can solve. In this question, he has there exist x, there exist. So 3 there exist you have. Then you have for all. So basically a sequence of there exist. This is the sequence of there exist. Then you have sequence of for all. The same template. The template is same, remember. Now, for this, he has given that this is given to you, that this psi, this has a model of universe containing 7 elements. This is given to you because see, there are 7 quantifiers. So that's why he has given that there exists a model of size 7. Now, these are the options. Very easily you can see that we can guarantee that there will exist a model of size 3. We can guarantee that. So this we can very easily guarantee that there will exist a model of size 3. So let's see the option. Let's see the option B. He's saying there exists no model with universe of size less than or equal to 3. So this is false, because we can guarantee that there exists a model of size 3. So this option B is false. He's saying there exists no model of universe size greater than 7. See, we cannot say this. We cannot say this. Neither we can say that. So actually, if you ask me for model of size greater than 7, then neither I can say that it does not exist, nor I can say that it exists. Both these information I cannot guarantee. So that is why this option C is also false. Every model has universe of size equal to 7. This is also false, because there exists a model of size 3. So that's why the answer will be A. Why this answer? Because He's saying there exists at least one model with universe of size less than or equal to 3. Because of this equal to 3, this A is the answer. Because of this equal to 3. Because of this, answer is A. If this equal to 3 is not there, let's assume this is less than 3. Let's assume this is less than 3. Then this is also not the answer. So that's why actually, because of this equal to 3, the answer will be option A. Now, you might be thinking, some of you might be thinking, actually, you must think like this, that we have seen this template, but what about other templates? So this template we have seen, like this template we have seen where there exists, so a sequence of there exist, okay, then a sequence of for all. So this template we have seen, but what about other templates? For example, you can have different templates. So let me give you one more example, and I will take a different template. Consider this question 3 we can take. So consider this formula G3, and this is for all x, for all x, for all y there exists z, p x y z. This is a different template you can see. Here we have for all x, for all y there exists z. This is our formula G3. Remember one thing, whatever template they give you, the method is same. The method is similar. You don't have to by heart these templates. I am not telling you to by heart these templates. No. You must understand the method. If you understand the method, then you can solve all the questions. Whatever template they give you, you can solve that question. For example, consider this template. For all x, consider this formula G3. For all x, for all y, there exists that px, yz. Now for this formula, assume that it is given to you that there exists a model of size 3. It is given to you. There exists a model of size 3. Now, my question is, can we guarantee that there will exist a model of size 2? Can we guarantee this? So this is my question. Now, right now, it will be a hard question for you. So I will solve it. But once I solve this question, and I have already solved many questions so far. Using all these concepts, using all this understanding, you can solve many more questions by yourself. So let me solve this question G3. In the G3, he has given that there exists a model of size 3. Now our question is, can we guarantee a model of size 2? So what I will do, first I will see what is this given information. The given information is like this. There exists a model of size 3. So let's take A, B, C. Okay, let's take this A, B, C. So okay, actually before we see this question, let's see easier question, because here we have 3 quantifier. Let's take only 2 quantifier, and then we will come back to this question. For understanding purpose, let me take this question first. For all x, there exists y, pxy. Consider this question. Okay. For this question, let's assume the given information is that there exists a model of size 2. This is the given information. And our question is, can we guarantee a model of size 1? Can we guarantee that? Let's see. So from this given information, what we have a model of size 2. Let's assume that is A, B. We have 2 elements, A, B. Let's assume this is that domain. So you have A, you have B. So then you, because this is a nested quantifier, for all x there exists y. So A, B. So he's saying for all elements, means for this, for all elements. He's saying there exists element. So consider this scenario that for this A, for this A, let's assume you have B, and for this B you have A. You can see. Consider this scenario. For example, for this A you have B, and for this B you have A. For these 2 pairs, P is true. So far we have only used the given information, remember, because this is the given information that there exists a model of size 2. Let's assume this is that domain. Okay, now you can see that this given information is true, because for this domain, for this interpretation, you can see this G4 is becoming true. So we have a model of size 2. Now what I will try to do, I will try to make it false. I will try my best to make it false. Like model, I won't uh, basically this model of size 1. I will check model of size 1. All the models of size 1 I will check, and I will see whether those domains of size 1 are model or not. So consider this. First, let's consider this domain 1. You can see this is a domain of size 1. Consider this. For this, can you guarantee that this is a model? Yes or no? Because we have single element, so you have to take a from here. Because this is a single element, so you have to take a from here. Now he's saying for all x, for there exists y, means for this a comma a, can you guarantee that p will be true? No, we cannot guarantee, because from the given information, this is the given information. For this a comma b, this p is true. For this b comma a, this p is true. But for this a comma a, we have no guarantee that this p will be true. We have no guarantee. So that's why for this domain, I cannot guarantee a model. I cannot guarantee a model. Let's take this domain. For this domain, can I guarantee a model? Again, because there is a single element. So let's take b here. Let's take b here. For all x, means I will have to take this b. There exists y, I have to take this b. For this b comma b, what about this b comma b? For this b comma b, can I guarantee that p will be true? Can I guarantee this? No, I cannot guarantee. You can just check it out. I cannot guarantee, because in the given information, for this a comma b, p is true. For this b comma a, p is true. But for this b comma b, I cannot guarantee that p will be true. So for this domain, I cannot guarantee a model. So for this domain also, I cannot guarantee a model. For this domain also, I cannot guarantee a model. So what it tells you? It tells you that we cannot guarantee a model of size 1. So this model of size 1, we cannot guarantee. This is how you can solve these questions. This is a different template we have taken in the GATE exam. So far only this GATE 2018 question was there, but they can ask you any template. If they ask you any template, this is the method you need to follow. Okay. You can also understand this question. You can also understand from the intuitive example. See, Sabrina is asking a very nice question, that if our original model is AABB, then there will exist a model of size 1. That is a very nice question. Remember in this question, he is basically saying that in this question, basically, okay, let me tell you, let me take it again. So this is your G4. For all x, there exists y, pxy. Now consider these two statements. I am making a statement 1 S1, and this statement is that if G4 has model of size 2, then G4 has model of size 1. Consider this statement. This is our statement that we want to prove or disprove. Remember. So this G4 is given to you, and for this G4, this is our statement that we want to look at. If G4 has model of size 2, let's assume this is the information that is given to you, that G4 has model of size 2. Then G4 will have model of size 1. Can we guarantee this? See, this implication statement is false. Why? Because we have taken this example. For this implication statement, I have given you counter example. And what is that counter example? I gave you this counter example, a comma b, such that like this. So this was the counter example for this statement S1. So what I can say? I can say that this statement S1 is false because I have counter example of S1. Are you getting this point? But remember, but remember, like the example you are telling me. So Sabrina is giving this example that what if this is that model? What if this is that interpretation? So you have domain A comma B. In this domain, let's assume this is the interpretation A, B. Remember, for this environment, for this model, for this environment, basically for this interpretation, this statement S1 is true. For this for this interpretation, S1 is false. So what you can say? You can say that S1 is false because we have counter example for S1. It's like this. Let me tell you. For example, you know one thing that view. If I make this statement, if you know the DBMS subject, in the DBMS subject we have conflict serializable schedule and view serializable schedule. Conflict serializable schedule and view serializable schedule. Now consider this statement, statement S1, that if a schedule, if a schedule is view serializable, then it is conflict serializable. Tell me, is this S1 true or false? Tell me. This statement S1, this is true or false? In the DBMS, you must have studied this conflict serializable schedule, view serializable schedule. Now, this is the statement. If a schedule is view serializable, then it is conflict serializable. This statement S1, this is true or false? So you can see this statement is false. Why this statement is false? Because we have counter example for this statement. Okay, we have view serializable schedules which are not conflict serializable. But now if someone tells you that consider this schedule, now consider this schedule, for example, this T1, T2, and consider this schedule, RA. Consider this schedule. Very easy schedule. There is no write operation here. Because there is no write operation, so definitely this schedule is view serializable. This schedule is also conflict serializable. Now consider this schedule. For this schedule, S1 is becoming true. See, for this schedule, S1 is becoming true, but we cannot say that S1 is always true because we have counter example. We have view serializable schedules which are not conflict serializable. Every conflict serializable schedule is view serializable, but there are many view serializable schedules which are not conflict serializable. So this is the point, that if you have counter example, then you can say that that statement is false. For example, here also our statement, this is our G4, and for this G4, if I make this statement that if G4 has model of size 2, then G4 has model of size 1, this statement S1 is false because I have a counter example. So intentionally I made this model. Intentionally I was making this model because I wanted to find out counter example. Intentionally I did not make this model because this model will not work as counter example. I want to make a counter example. I told you I want to prove this false. I will try my best to prove this false, and I have proven it false because for this environment I have a model of size 2, but I cannot guarantee a model of size 1. So that's why this statement S1 is false. Sabrina, is this clear? So don't, like, always try to find counter example. If you cannot find counter example, if you can prove that there is no counter example, then you can say that this statement S1 is true. Like in the previous examples we have seen. Okay. For example, in the previous example, we have seen this example we have taken. There exists X for all Y. This was the example we have taken. For this formula, I can make this statement. What a statement I can make, that if if there basically if there exists a model of size 2, then there exists a model of size 1. I can make, now this statement S1 is true because there is no counterexample. Whatever you do, you try your best to make this statement S1 false, but you cannot make it false, because if there exists a model of size 2, then there will definitely exist a model of size 1. So that's why this G1 is, this statement S1 is true. So this is the point. Now consider this, we were having this example, for all x, for all y, there exists Z. For this is similar question to the previous question. In the previous question, we had this, there for all x, there exists y. This was the previous question. For all x, there exists y. In this question, we have for all x, for all y, there exists Z. And in this question, he has given to you that there is a model of size 3. Can we guarantee a model of size 2? Can we guarantee this? Let's see. I will try to make it false. Remember, always try to find counterexample. If you can find counterexample, then then statement is false. If you cannot find counterexample, if you can prove that there is no counterexample, then that statement is true. So for this example also, again, what I will try to do, I will try my best to use this information, to use this given information, and to not have a model of size 2. I will try my best. So let's consider this situation. A, B, C, A, B, C, A, B, C, because there are three quantifiers, so A, B, C, A, B, C, and so on. He's saying for all x, means for A, for B, for C. Here also for all y, means A, B, C, there exists a Z. Now what I'm going to try to do, I'm going to do like this. For all, matlab for this A, so for this A comma A, basically for this A comma A, what you take, there exists a Z. For this A comma A, there exists a Z. So let's take that Z to be B. For this A comma A, take that B. Okay. Okay. So sorry, wait a second. What you do? Let's not write all the things, but let's only write the things that we will require. For example, for this A comma B, because for all means for every pair of these two things, means for this A comma B, let's take, there exists a Z. So let's take that C. And for this A comma C, let's take B. For this B comma A, let's take C. Are you getting this point? What I'm doing? I'm doing like this. For every pair here, I am taking a different element here. For example, for this A comma B, I am taking C, because he's saying there exists a Z. So for this A comma B, this C is there. For this A comma C, this B is there. For this B comma A, this C is there. Okay. For this A comma C, B is there. Like this I am doing. For this C comma A, B is there. So like this I am doing. Okay. You can see that I have satisfied this given condition, because for this A comma B comma C, of course, some more things are there. You can add them, but you are getting the idea what I'm trying to do. I'm trying to do like this. For this pair A comma B, I am giving C. For this pair B comma A, I am giving C. For this pair A comma C, I am giving B. Okay, like this I am doing. Okay. Now, also for this pair B comma C, I am giving A, like this. After doing this, the given condition is satisfied. Okay. Now, let's find out whether there exists a model of size 2. So take A comma B, for example. For this A comma B, can I say that this A comma B will be a model? Let's see. So this is A comma B, this is A comma B, and this is A comma B. See, for this A comma A, what exists? For this A comma A, let's assume C exists. A comma A, let's assume C exists. So like whatever you do, the point is that what will exist for A comma B? That is the point. That is the question. What is there for A comma B? For this A comma B, what is there? You can see that for this A comma B, we have C. But in this, we don't have C. So for this A comma B, we cannot have anyone here. We cannot guarantee anyone here. We cannot say that for this A comma B, A will be there, or for this A comma B, B will be there. We cannot say that, because in our given condition we are taking, for a comma b we are taking c, for b comma c we are taking a, for c comma a we are taking b. So that's why you can say that for this pair a comma b, for this pair I don't have anyone, I cannot guarantee anyone. So that's why I cannot guarantee a model of size 2. Sabrina, your statement is false actually, because you are saying that there does not exist a model of size 2. Remember, there may exist a model of size 2, but we cannot guarantee it. So there may exist a model of size 2, there may not exist a model of size 2. So that is the correct statement. If we say that there exists a model of size 2, then that would be a false statement. If we say there does not exist a model of size 2, that also will be a false statement, because we cannot guarantee existence of model of size 2. It may exist, it may not exist. I have proven it. For example, if you take this interpretation like this, if you take this interpretation, then there does not exist, then we cannot guarantee a model of size 2. That is the point. So you can see. Is this point clear, Sabrina? So like this you can do. So actually, intuitively, if you want to think about it, for example, this example we were taking, for all x, there exist y, and this pxy. This example we have already seen. For this example, the given information that there exists a model of size 2, and we were asking the question, is there a model of size 1? So you can again intuitively think about it. See, in this question, what he's saying that there exists a model of size 2. Let's assume this is the family. So this is the family of two people. Okay. Rajdeep, no, you cannot say that, because we have taken, see, it will depend on the question. What is your formula? For example, we have already taken this type of questions. For this type of question, for this question, model of size 3, model of size 3 will imply model of size 2. If there exists a model of size 3, then definitely there will exist a model of size 2. Are you getting? So it will depend on the question. So once you practice it enough, once you take different situations, okay, once you understand all these, once you practice it enough, automatically you will get it. See, for this question, a model of size 3, if you have, then you can guarantee a model of size 2. So you can see. But for this question, for all x, for all y, there exists z. For this question, if you have a model of size 3, then you cannot guarantee model of size 2. So it will depend on the question. This is one possible question. This is another possible question. There are many different questions are possible. For example, this is another possible question. For all x, there exists y, for all z. This is another possible question. For example, this is another possible question. There exists x, for all y, for all z, there exists m. This is another possible question. So there are many different, many different cases are possible. That's why I'm saying you, and that's why I'm telling you that don't by heart the templates. Just understand the procedure. There will exist, but we need to choose the elements correctly. See, this is what I'm telling, that if you consider this example, there exists x, there exists y, for all z. Consider this example. For this example, if you have model of size 3, then definitely model of size 2 will be there. So whatever element you choose, whatever connection you make, whatever you do, that is your wish. But if you have a model of size 3, then definitely there will exist a model of size 2. So whatever connection you can make, that is your wish. You can make any connection. You can take any 3 elements. You can do anything, whatever you do. this model of size 3 will definitely imply model of size 2 for this question. We have already seen this. So, like, okay, don't confuse. It's just a matter of practice, because this is the first time maybe many of you are studying this topic first time, because no one teaches these concepts. But in the GATE exam, already there are questions. Two questions are there. In 1991, there is a question. In 2018, there is a question. And this is the recent questions. So that's why, because no one teaches these concepts, so that's why you are confusing. But don't confuse, just practice. Okay. If you have any doubt, you can re-watch this video. You can try to re-watch it, and you can try to solve each question by yourself. First, try to solve each question by yourself, then you will automatically starting to get all the concepts. Okay. If you have any doubt, then you can re-watch this video again, or you can ask me. You can ask me any doubt, whatever doubt you have. You can make your own question, and then you can ask. So whatever question you will make, you can make like this: there exists x for all y, there exists z. Like this you can make. Okay, for this question you can try to solve. So you can make your own question, and you can try to answer those questions. And if you want to confirm whether your answer is correct or not, then you can ask me. Okay, I will let you know whether your analysis is correct or not. Okay. So what I was saying, yeah, I was giving you the intuition for this question. Like, for this question, we have already seen that if model of size 2 is there, then we cannot guarantee a model of size 1. So the intuitive idea is this: because it is given that there exists a model of size 2, so let's assume this is the family a comma b. These two people are there, a comma b. This is a family. Now, for everyone there is someone, means basically everyone, like, for example, let's assume that whenever a is in trouble, then this b is there for him. So for this a b is there, and for this b, a is there. Like, basically, in Hindi if I say, वो एक दूसरे को संभाल रहे हैं, मतलब ए को संभालने के लिए बी है, बी को संभालने के लिए ए है. ठीक है, ये सिचुएशन. लेकिन अब अगर मैं कहूं, if I say, if I want to say whether there exists a model of size 1 or not, so I cannot guarantee that. Because if you make it alone, let's assume that unfortunately this b has died. Okay, this b is dead, unfortunately this b is dead. Then you can see that there is no one to take care of a. Now if a is in trouble, then there is no one for a, because ए है, ए वो खुद को नहीं संभाल सकता. ए को संभालने के लिए बी था, बी को संभालने के लिए ए था. ए खुद को नहीं संभाल सकता, बी खुद को नहीं संभाल सकता. तो अगर आप ये कंसिडर, इफ यू कंसिडर दिस सिंगल एलिमेंट डोमेन, then you cannot guarantee that let's assume this p x y is basically x takes care of y. X takes care of y. So now I cannot guarantee that a can take care of a. Similarly, if I have this, then I cannot guarantee that b can take care of b. So this is how you can intuitively understand all these situations. But we can guarantee model of size 2 if model of size 3 is present. Okay, yeah, that is a nice question. Let's try to solve it. For all x, there exists y, pxy. Now you are making your own question. That's a nice thing. This is how you should, like, this is a nice approach. So let's consider this. So Rajdeep has given a very nice question. He's saying that for this g1, let's assume that it is given that there exists a model of size 3. Let's assume this is given to you. Now, can we guarantee that there will exist a model of size 2? Can we guarantee this? Let's try. So there exists a model of size 3. Let's assume that is a comma b comma c. So you have a comma b comma c, and this is your a comma b comma c. So he's saying for everyone there is someone. Let's assume for a you have b, for b you have c, and for c you have a. Let's assume. So for a you have b, for b you have c, and for c you have a. Consider this situation. So you can see that for everyone there is someone. You can see, basically, so far I have used this information, this given information I have used. Nothing else I have done. I have just used this given information. but I am intentionally making this situation. You might be thinking, why I am taking this particular situation, why I am not connecting A to A, why I am not making B to B. I am intentionally taking this situation. Okay, now let's see whether there exists a model of size 2 or not. Let's see. So consider this A comma B. Consider this. Okay, can I say that for this A comma B, can I guarantee that this G1 will be true? Can I guarantee that? Anyone? Try this. This is a nice question Rajdeep is asking. Rajdeep, try this. So this is the situation. This is the given situation. Now, can you guarantee for this domain A comma B? Can you say that this will make a model? Can we guarantee a model? Anyone want to answer? So you can see for this, you can see he's saying for all x means for everyone there is someone. So for A there is B. Okay, that is okay. That is okay. For A there is B, because for A there is B. But who is there for B? For B, who is there? See, in this given situation, for B there is C. B को संभालने के लिए C है given situation में, लेकिन अब B को संभालने के लिए कौन है? Can you guarantee that A can take care of B? No, you cannot guarantee. Maybe this is the situation. Assume that this A, B, C. Assume that this A loves B, so A can take care of B. B loves C. B can take care of C. C loves A. So it's a triangle. It's a love triangle. So you can see that if you take these two people, A comma B, let's assume unfortunately C is dead. Let's assume unfortunately C is dead. Then now, of course, A can take care of B, but B will not take care of A. We cannot guarantee that B will take care of A. He may or he may not. We don't know. But we cannot guarantee. That is the point. We cannot guarantee that for B there will be A. Whenever B is in trouble, A will be there. We cannot guarantee that. Okay. So you can take B comma C also. You can take A comma C. Whatever two element domain you take, you can see that we cannot guarantee a model of size 2. Radhik, is this clear? So now I think now you are getting the point. Now you are getting this concept. Now everyone, I think after this example, I think everyone is starting to get the concept. Let me know. Is this point clear? Okay, so this is enough. I think all the concepts I have already covered. This is the GATE 2018 question, and we have done it. Many additional questions we have solved. And this is GATE 1991 question. And this is a very easy question. Okay, you can try to solve it. Here he is asking, do we have finite model? Finite model means a model which has finite domain. So this, you can take it as homework, or maybe I can solve it in the next lecture, but take it as homework. Okay. If anyone has any doubt in this question, first you try to solve it. After that, if you get any doubt, then you can ask me. And in the next lecture, in the first 5 or 10 minutes, I will solve this question. And after that, we will start the next chapter. And the next chapter that we will take is graph theory. So this is the next chapter that we will take. In the next class, graph theory we will study. Many tricky questions, many tricky concepts of graph theory we will study in the next class. Okay. So from the mathematical logic and propositional logic point of view, all the concepts I have covered. Okay, every concept I have covered, but of course, some concepts, if you want to like study this complete discrete mathematics, then I have already covered this discrete mathematics. You can enroll in the course of GATEFORUM. There I have already taught it. Okay, so in like in the discrete mathematics course, discrete mathematics course of Gate Forum, I have already taught many concepts. All the concepts I have covered, and these small concepts were remaining, like this model concept and these infrequent concepts. Like I will call them infrequent concepts, because they are not coming in Gate exam frequently. Very infrequently they are asking these concepts. So these concepts were remaining in this discrete mathematics course. So now I have covered. Now every concept has been covered. No concept is remaining. Okay. So if you want to join this, like if you want to study this discrete mathematics course, then you can basically enroll in the Gate forum. There I have taught it. Okay. So thank you everyone. Okay. Bye.